Hello viewers, myself is Dr. Vadiraj Tangod, Assistant Professor, Sri Jagadguru Tontadariya Government First Grade College, Mundarli. In this video, I am dealing with the thermodynamics, review of the some of the basics which are concerned with this thermodynamics chapter. This is for program of BSc Physics subject for second semester, and this is first session and discussion is thermodynamics review of the basics. This is complete syllabus of thermodynamics. It contains 4 chapters: heat engine, entropy, enthalpy, and Maxwell thermodynamical relations. To deal all these topics, we are necessary of certain basic concepts which are required for the thermodynamical discussions. So therefore, we want to discuss review of basic concepts in thermodynamics. Learning objectives for this session is to know the concept of thermodynamics, to understand the concept of heat and temperature, and differentiation between these two parameters. Knowledge of basic zeroth law of thermodynamics, idea about the basic terminologies in thermodynamics, knowledge of first law of thermodynamics. And outcomes from this today's discussion is knowledge of thermodynamics, understanding of basic definitions of terminologies used in thermodynamics, idea about work and internal energy, concept of first law of thermodynamics. Prerequisites to discuss this discussion is concept about heat and temperature, concept of zeroth law and laws of thermodynamics, thermodynamical applications in various fields. And discussion is divided into the following contents. It contains introduction, scope of the thermodynamics, some important definitions, work, internal energy, heat, and first law of thermodynamics. Now, thermodynamics. Basically, the question will arises, what is thermodynamics? Thermodynamics is a branch of physics. It deals with the study of heat, temperature, work, and also the physical properties of matter. In a broad sense, thermodynamics deals with the transfer of energy from one place to the another place and in one form to the another form. The key concept of heat is the form of energy corresponding to definite amount of mechanical work. And this branch of physics, thermodynamics, it has been started by Saudi Carnot, and hence we can rightly call him as father of thermodynamics. He is Saudi Carnot, and the use of this thermodynamics is in various fields like physics, chemistry, physical chemistry, biochemistry, chemical engineering, mechanical engineering, and also in meteorological sciences. Some important definitions. The first and foremost definition required is system and surroundings. The thermodynamic system is that part of the universe which is being subjected to thermodynamic scrutiny, and everything else in the universe constitutes the surroundings. The differentiation between system and surroundings is marked by a boundary called boundary, and it is shown in the red dashed line. Now, the systems are of three types. One is called open system, closed system, and isolated system. Open system is the one in which it can exchange the matter and energy with the surroundings. Examples is air compressor. Closed system is the one it can exchange only the energy but not the matter with the surroundings. It is called closed system. Example, gas enclosed in a cylinder expands when heated. It moves the movement of the piston. As a result, the transfer of a heat energy takes place but not the mass. It is called closed system. And isolated system is the one it cannot neither transfers the energy nor the matter with the surroundings, is called isolated system. This can be represented by a block diagram like this. Isolated system is the one it cannot share the energy and matter with the surroundings. Closed system is the one it can exchange the energy but not matter with the surroundings. Open system is the one it can exchange both energy and matter with the surroundings, is called open system. Now, zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies A and B are separately thermal equilibrium with the third body C, then A and B are also in thermal equilibrium with each other. We consider two systems A and B insulated from each other but in good thermal contact with a common system C. Systems A and B will attain thermal equilibrium with a third system C. Here, pictorial representation of the zeroth law of thermodynamics. In figure A and B are the two systems. They have been kept in an insulating part and it cannot share the energy and matter with any surroundings or with any systems. So A and B are separated by the insulated portion. A and C are thermally in contact. Similarly, B and C in thermally contact. If A and C are thermally equilibrium with each other, and also B and C are also thermally equilibrium with each other, so according to zeroth law of thermodynamics, A and B are also thermodynamically equivalent to each other. Therefore, it is represented by the figure B. Therefore, in figure B, A, B, C, all of them, they are thermally equilibrium with each other. Therefore, A is thermally equilibrium with C, B is also thermal equilibrium with C. It implies A is thermal equilibrium with the B. This is called zeroth law of thermodynamics. Now the insulating portion is removed. The systems A and B are brought into thermal contact. We find that there is no further change. This means that systems A and B are also thermal equilibrium with each other, and this is known as zeroth law of thermodynamics. Thermal equilibrium. For a system to be in thermal equilibrium, there should be no temperature difference between the parts of the system or between the system and the surroundings. Suppose thermal equilibrium can be depicted by the picture here. If one system is 100 degrees Celsius, another system is 0 degrees Celsius, if we keep in contact with the both system, after certain few minutes or few hours, both the system attains the thermal equilibrium condition, that is both the systems having the temperature 50 degrees Celsius, 50 degrees Celsius, that condition is said to be thermally equilibrium with each other. Work. The term work refers to interchange of energy between its system and its surroundings. If a force F produces infinitesimal displacement ds, then the work done by the force is given by dW is equal to F dot ds. Consider a constant mass of a gas in a thermal cylinder container with a movable piston. Initially, this system be in equilibrium with its surroundings and has a temperature and has a pressure P1 and volume V1. heat can flow into the system or out of it through the walls of the system. Suppose the gas is expanding against the piston, work done by the system and reaches final equilibrium state characterized by the pressure P2 and volume V2. The work done by the gas on the piston is found by the indicator diagram. The graph between pressure and volume has been drawn. To calculate the work is the area under the curve ABCD. Internal energy. The energy content of a system is called its internal energy, and it is the sum of the following forms of energy of the system. Kinetic energy is due to translational, rotational, and vibrational motion of the molecules, all of which depend only on the temperature. Potential energy is due to the intermolecular forces, which depend on the separation between the molecules, and the energy of the electrons and orbit. All these kinetic, potential, and the energy of the electrons and nuclei, it constitutes the energy called internal energy of a system. If the state of a system is changed from initial state 1 to final state 2 by supplying heat Q to the system, and if W is the work done by the system during the change, then increase in internal energy of the system is given by U2 minus U1 is equal to Q minus W, where U2 and U1 are the internal energies in state 1 and 2, and Q is the amount of heat and W is the work done by the system. Heat. Heat may be defined as the form of energy, and heat may also be defined as energy in transit. It flows from one point to the another point. If the flow of heat stops, we cannot use the word heat. That is, the word heat may be used only when there is transfer of energy between the two or more thermodynamic systems. When two bodies of different temperatures are placed in contact with each other, the two temperatures approach each other and after some time both become equal. This phenomenon is described by the first law of thermodynamics, the flow from one body to the another body. Thermodynamically, this flow of energy from one body to the another body on account of difference of temperature between them is called heat. If we keep the hot temperature at one end, cold temperature at the other end, if we make the thermal equilibrium with each other, after a few minutes, both the hot and cold ends, they becomes a same temperature. That condition is called thermal equilibrium condition. Now, first law of thermodynamics. The amount of heat Q supplied to the system is equal to the sum of increase in internal energy of the system and the external work done by the system. In symbols, Q is the amount of heat supplied to a system. It is utilized for the two purposes. It is to increase the internal energy from system 1 to system 2 plus work done by the system. For a very small change in the system of the system, the law is expressed in differential form as dq is equal to du plus dw, where dq is the infinitesimal small change in heat, du is the change in internal energy, dw is the amount of work done, that difference is dw. So this is all some review of the basics of thermodynamics in our first discussion. So if you may have any questions or any doubts, you may feel to write in a chat box, or you can send it by through chat, WhatsApp chat, or through the mail, or whatever may be. So this is all my today's discussion. Thank you one and all for all of you. Thank you one and all.